Yes.
Look for data science. What's the name of the channel?
It's transient dynamic.
Huh. It does not show for data science.
Yeah, they don't have a tag yet for data science.
Right, but I'm saying
But
if you just search for data science.
Yeah, I wonder whether it might take a while for it to, because I don't think there are other people really doing it.
Yeah, there's only like 7 things that pop up when you type in data science. We should pop up on this, yeah, especially with the popularity of the term. Like, this is a good way to reframe the thing behind it.
Yeah.
So I am definitely watching.
So you found it?
Mm-hmm.
Okay, good.
But I did have the benefit of knowing the...
Yeah, so I'm going to put in, just make sure that works. Cool.
Where are you? You see the eye scanning? Is that where you did it?
So yeah, we're working with Chris. I'm Rob, and we have two guys called Chris here today.
Oh, hi. Hey. Lots of Chris's in the room.
Yeah. And we're going to be working on some data models for a data science hackathon that we're coming up with.
Cool.
So we want to build some tools. First stage is to make some tools to build the things that we need, and want to come up with some classes in Python using Jupyter Notebook mainly to create the data that we'll need for a data science hackathon, to an event of that kind to use as a sort of test suite.
What would you say the overall point of the hackathon is?
The hackathon is intended to give people an educational experience that is quite realistic in terms of the kinds of interactions that they'll have cross-functionally in an organization surrounding data. And the twist is that we will have gamified it so that it nominally will actually look like almost like a board game in some respects. But it'll be designed so that the content will be very much like actual kind of data science work, and cross-functionally too. So it will involve aspects of design and journalism and things that get involved with marketing and stuff like that too.
It's also, I would say, an exciting part of the project is avoiding some of the pitfalls that we've seen at hackathons, where there's not necessarily a clear direction or clear outcome, or people banging their heads against the wall. With this, we'll be focusing on creating an environment, a story, a setting for people to learn, and it's not going to be the blind approach. It's going to be something that's like a parameterized environment, guided, with a clear outcome and clear ways to measure success.
Yeah, indeed. So next time we'll have some microphones for them to be clearer, so hopefully that's audible. So we came up with a model, very, very sketchy model that involves some sort of sci-fi environment to play in, and we're going to have some star systems and some planets, we think, and there'll be some data associated with them, some of which is static, and some of which is sort of time series data. So there's static attributes of things, and right now we are just building a proof of concept. So none of these things are necessarily fixed. We are looking to just sketch out what kinds of sort of tools we need to even put data like this together in a procedurally generatable way, so that we can alter things later as we need, and so that we can fit the components together. So we're going to be making a lot of time series data. So we are interested in providing, say, a history of incidents or of attributes to these planets. It could be things like temperature, ranges over time, or things like their population if they're inhabited, or a history of past events, depending on what kind of sort of model we have in terms of what you're trying to detect as a group.
How are players going to be interacting with that?
Yeah, so players are going to be provided with access to databases essentially during the event, and they will need to query the data and explore it. We're not sure how much we give them in advance about the structure and schemas and so forth, but they will essentially just have a database, and it will be up to them to draw the data out of it and figure out how to turn it into insights. So it'll be things like finding patterns, looking for, models, like data models, doing statistics that will help them to detect patterns and figure out things that are true positives, false positives, and so forth. Yeah.
Where are we going to start?
Yeah, so I think what we're going to start to do is maybe write a couple of classes that, because we're doing this completely off the cuff, we don't really have a lot of plan right now as to how this stuff will look. So we're going to build some classes for the planets and start filling in what it might take to procedurally generate some of these types of attributes. So we've got attributes like size of the planet, its location from the star. We're going to keep it pretty simple. I think we're going to number the planets in order from the sun, 1 to n. And then we might come up with some model for generating some floating point real numbers for percentages of content of some chemicals that we might think are appropriate for measuring whatever thing we come up with later. So how's the volume? You probably can't tell. Yeah, we'll figure it out later. So we're going to need, we want star systems, and we're going to work in Python 3 using Jupyterlab, and we're going to think about the kinds of things that we want to have in a star system. So the main thing is that there's going to be an ordered number of planets, right? So yeah, probably going to have a list at the beginning, and we will decide how to populate this with maybe a factory function later. And this may even, well, the only other thing I think we might know in advance is that we'll have coordinates. And so we're going to use a 2D space, we've decided. So we might pre-populate those coming in as a...
That gives us alpha and delta quadrant and things like that too.
Maybe. I mean,
if we want to go there.
we might have kind of neighborhoods. That was the idea we talked about before. Maybe having neighborhoods of things as a different grouping on top. But certainly, at least we'll start with x and y coordinates in some 2D space.
Most importantly, we'll be able to show a map.
Right. So maps will be a thing because we want people to be able to practice using geographic map-based data tools. Yeah. Yeah, that would be groovy.
And they're shiny.
Yeah. It is. It'll be nice for people to do visualizations with things, put heat maps on stuff and so forth. So, given that is my simple base class, I'm going to think about what it will take to have a factory function that will put in number of planets. So, I'm going to think about making a function. And it's going to return a system that we're going to build, right? So the system is going to be type star system, and we're going to have to generate an x and y for it, which we obviously don't have yet. So we need to, put in placeholders here. And then the planets. So one of the first variables that or parameters that we need to set is the number of planets. And I'm not going to put in, this is for internal use, right? This is for us to generate stuff. So I'm not really worried about a lot of boilerplate around checking that that's an integer and so forth, right? Because this is all internal stuff. So we have a number of planets, and then we'll have to generate planets. So that's a different class that we'll come up with in a minute.
It's probably a good caveat across the board, right? This is not meant to be like production code.
Yeah, none of this is production code. It's purely exploratory.
Yeah.
Just getting our head around the kinds of systems that we might want to build out later, even potentially offline. But we just thought we'd share this as part of the process. So I'm going to add a class for a planet. And music seems pretty appropriate right now. So a planet is going to have a position in the star system. We've decided to keep it simple. It'll just be the order in the solar system.
How are you defining that?
That will be defined down here when we create the star system. We will, so that a list has an actual ordering on it, which is indexed from 0, and so we might also number the planets from 0 to avoid translating, right, all those indices as we go. So planet 0, I guess, we'll sort of arbitrarily call out the innermost one, and that might be something worth commenting in the code. And we might even say just indexing into a list for now, just so that's clear why we're making that choice. So we've got the integer position, and that's also, I guess, we can just pull in. So we might turn this into a dictionary later, in case there are defaults for things and things that are optional. But we're going to start just listing some of them out and making a long list of parameters that is not necessarily best practice. So we said we'd have size and length of year, and let's just pick one. We call it year, and we'll just call it oxygen percentage. We'll just stick to that for now. So I'll just move these things into attributes of the object.
Question is, so do we want year to just generally be relative to position?
So that's one of the questions that we will want to tackle, because theoretically, there are probably some commonalities across star systems that, like ours, right, where there's a lot of alignment of stuff in the same plane, and that maybe most of the orbits are quite similar, and that probably does provide some uniformity or some structure to predict relative year lengths.
Outliers, though. So.
Right, but there's going to be outliers. So I think that the position will absolutely be a parameter to a model of generating the year, and that you would hope that it would mostly grow as you get further away. But I think it'll be more. It remains to be seen how interesting that variable might be, and how important it is for that to be realistic.
Yeah.
But I think that is the baseline is that we can make it linear or something from the distance.
Yeah, if we have just an assumption on orbital speed and position, let's say it correlates to sort of hard number distance, like 1 is always 70 million miles and 2 is 93 million miles, yada yada yada.
Yeah, and we can abstract that enough. I don't think we're planning to do any actual calculations on
orbital dynamics come into play. Come on.
Yeah, right. We could, but I don't think that won't be the most fun for us right now. So, but yes, we will absolutely use the position as a factor in generating the year, and that's part of what we're going to do today. Is come up with some simple models for that. So you see, we might build a star system first, and before we return it, we're going to populate it with the planets. So we're going to iterate through the number of planets like this.
How are you going to divvy up planets per star system?
How am I going to divvy up
planets per star system?
In what way? How?
Like just equally subdivide them, or are you going to you're just going to keep picking out of the list until you're done?
I'm foreseeing just creating each star system's planets as an individual call to something.
Okay. So you just keep going until you get the number?
Basically, yeah. Yeah. At least, that's my initial feeling, is just keep going until you've got enough. So we're certainly going to need to build a planet object, and then we're going to need to fill in the position. So the position is going to fall out naturally from this range object that will iterate through 0 to n, or 0 to n num-planets. So that gives us the position, and then we're going to need sizes, years, and oxygen percentages. So this gives us a framework for seeing a simple type of loop that will populate one star system with n planets. Okay, so the star system, so I guess this coordinates is the coordinates of the star, and everything else is assumed to orbit around that star. So size, I'm thinking that we would go with well, yeah, I was thinking of maybe abstracting it and having a floating point maybe between 1 and 100 as a size indicator of radius or whatever. I mean, it doesn't really matter right now, right? It's just...
I might just do like an enum and just have like different classes, 5 classes.
Yeah, we might have classes too, right? So that we might go that route.
If we go with 5 size categories and each number corresponds with an actual radius, then I think we've done the job.
Yeah, either way. And we might need both anyway. So I'm gonna build, that's a good maybe segue to build another component that we're gonna need, which is gonna be to generate numbers in a range. And I think we're going to need to keep track of what these ranges are, because we might need to parameterize them as part of setting up a project. So I'm going to think about making a class here to store this information so that it's all kind of trackable. We're probably going to need a name. I mean, that probably would belong to the class, and then we're going to have a low and a high value. And I don't think for now, to keep it simple, that we're going to discretize that. We'll just have arbitrary float values between, for this class at least. But the other important thing would be the distribution that we draw from. And that's going to be where things get complicated again. Because the distribution will be how we actually generate numbers in that range. So for the simplest case, you just use a uniform random number generator, and they're equally likely between the low and the high. But it gets interesting and more useful and more realistic if we draw from alternative distributions that exist and put in some bias and trends towards different types of things. So more of that to come.
That's where it gets really fun too.
Yeah, I think that's also where it gets fun from a data science perspective. So this class is also kind of a factory class, because really you're going to have a function that actually generates values from this distribution. We certainly haven't put a lot of thought into this yet, so this distribution is probably going to be related to a class that I found in an open source project called Stochastic in Python. So you can pip install this class, this library, and it builds on SciPy. So SciPy is full. Actually, they're probably NumPy these days. They're full of these statistical distributions, and this just provides a wrapper on. It makes it nicer to build some of those types of distributions. So I'm going to assume that this is a object from the stochastic.
What does it give you that NumPy doesn't?
I didn't read it closely yesterday. I just kind of assumed that it added value since it popped up high on the Google list. Yeah, and I haven't used the NumPy ones for a long time. We can get to that later because we're going to have to dive into it anyway. So we'll probably figure out exactly what it adds later. I think among other things, it probably simplifies the interface for building them a little bit. We'll see. Yeah, we may backtrack on that if it turns out it doesn't add so much. Well, actually, now might be a useful time to figure out what do we need. So I'm going to leave that for now as a placeholder. So for each planet, coming back to this star system loop here, we want to generate a size. And so we might have an instance of float range which is specifically for planets, right? So it will subclass it, planet size, and we will be maybe this actually probably is pre-made. So let's see, down here then I'm going to make an instance, and its size is a float range. Oops, thank you, late autocomplete. And we're maybe going to try out taking that from 1 to 100, and we might make that uniform. Okay, so I'm going to go back and hope that appears. Hooray, autocomplete worked. So that's going to be a distribution that I have no idea, but fortunately, nope. I thought it was going to autocomplete. So there are classes in here, but it's not showing them to me, and I'm probably doing something wrong. Oh, try Shift Tab. No, I blew it. All right. This might be the kind of thing you would put in a console, actually. Let's see. I've forgotten how to make a console. Here we go. I wanted to make a console from... Oh, here we go. New console for Notebook. That's what I wanted.
Why are you doing that?
So it's a nice little way to not pollute your notebook with things that you're doing on the side. So for instance, right now I just need to check out what is inside of Stochastic. And of course it's one of those types of packages that doesn't tell you things. All right, so that needs to be Googled, but you know, I'd have to go back and delete that from my notebook if I put that into a cell, and so I'm just trying to avoid cluttering. And it's kind of a good practice just to have a little thing on the side that you can use, which is also connected to the same namespace.
Actually, I missed what you did to bring up that tab.
Yeah, so I thought, because you can make a console just from a new launcher, but unless I'm forgetting, the console that you get is just a fresh instance of Python. Instead, if you right-click on a cell and new console for notebook, that will create one that has its
In context.
Yeah, so it's got the context. In other words, it shares the namespace with the kernel running this particular notebook.
Well, good. Now I don't have to create a bunch of cells to figure out what things do and functions do.
And it's just nice to have it around, you know.
It's nice.
It's a scratch pad, exactly. So, and this is a feature of Lab, JupyterLab, rather than the notebooks. So, yeah, but it turns out I still need to look it up. So we will quickly figure out stochastic.
basically the question of whether or not it offers distributions above and beyond NumPy.
Yeah. I used it a couple of days ago for something for the first time, but...
What'd you get out of it then?
Well, I didn't do anything comparative with NumPy, but I did just pull out the Poisson distribution for that initial test that we looked at. A lot of what these packages do is they just unify interfaces to things that sometimes are legacy. A lot of older stuff in NumPy, I haven't kept up with some of the recent trends, but a lot of the older packages in sub-packages in NumPy were inherited from really, really old code, and they had very inconsistent interfaces, and there's been a long-running effort to unify those interfaces, but in the meantime, some people have just gone ahead and written another wrapper over these things. So that might be what it is, but they may have also added some other stuff that I'm not aware of. There's quite a lot of, like there's some pretty funky diffusion processes in here, like the Ornstein-Uhlenbeck, which is very valuable. I don't know whether NumPy has that, so we'll see. But I can't even see if it supports a simple thing like uniform. Nope. So that's not a lot of value. So we're going to subtract one Chris at this point.
He's Chris.
Chris is to Chris.
I'll message you later. Thank you very much. Yeah, so this doesn't have a uniform process unless I might be missing somewhere that they've named something, but that's okay. So we'll figure that bit out later. I am going to start with a uniform process, so we're going to have to pull that from somewhere else. So I will import random. And in random might do the same thing to us, but no. So this has, you can tab this and see all of the good stuff in here. Oops. So they have uniform, and then if I open the parens, I can get a random number in a range, and I'm basically just going to use that. So let's see. That's not a distribution, unfortunately. That's going to complicate how we build this, since we can't use the same type of class. So the thing with the random, I guess I'd have to wrap it myself if I can't find it elsewhere. I want it to be a class that I can pass. Think about the way that stochastic would be used. Let's look at the example down here. I mean, they're all going to have different types of parameterizations, so I suppose it's okay. I can just pass the function and then I'll provide the parameters. Maybe it's okay. Maybe the function is a good stand-in for the distribution. Because then what will happen when I decide to make an instance, maybe call this generate instance. It's really an instantiation, but I don't really want to type all that out. So I'm going to take the distribution, I'm going to call it and expect, because we know this is a float range, so we'll just be making we'll draw from that distribution between low and high values, and we'll return that value. That's all it needs to do. All right. So then planet size now is a instance of that class, which means I could have made it a callable class, but just to be explicit, because it doesn't really do anything else but get called like this. But when I'm ready, I'm just going to pull an instance out from that class, and that guarantees that I'm going to get a number that's consistent with how other planets are defined. So if we want to change all planets in our data model, then all I have to do is update this named class, so it's very clear where these numbers are coming from. We have a lot of control that way. So that'll get us a number, and I should probably test that, but I'm feeling fairly confident about it. So let's just test it in this console down here. Oh, the Google Hangout box is in the way. There we go. Yeah, so there we go. Pulled out a number for us. So that's just a uniform distribution. That's totally fine right now. We can refine that later to make it more interesting. So we've got a size. And then the year, we said might scale with the distance from the sun. So we don't have a model right now for the distances. You know, in real life, we might imagine those distances get larger and larger, right? So it's not linear. But let's just make a linear model as the first pass, and that way we can always make it more interesting later. So, you have any questions, or is that clear?
Yeah, that makes sense. Yeah, it's going to be interesting to see, like, as we build these attributes, ultimately how that plays into some of the encounters and incidents that players will
that's right. Well, that's why the reason I want to add this kind of heavyweight infrastructure. It seems like a lot up front to just build out some simple numbers for things, but it's gonna trust me, it's gonna make it amazingly flexible and easy to change and try out experiments when you want to balance these values as part of gameplay.
Yeah,
you'll have a lot of control, and things will just be organized really, really well, and it'll make our life easier.
Yeah, it's good to think through that so that we don't end up with a bunch of nonsensical events like
or just an Excel sheet that's full of individual numbers that we've pulled out of a hat. And say, let's have 3-star systems, and let's just give this number 1 and this one number 3.5, and then later we learn that we don't want it that way, and you have to like hand edit them all again. It does take a bit more time at the front, but it's also, writing code like this is a great way to really organize your thinking around what you really need, and it makes things very deliberate. Naming things is hard, so making sure that making sure you really want a thing before you try to name it, it's a good barrier of entry to creating a thing. So in fact, to begin with, if it's really going to be linear, then we're essentially a linear model is just going to say that the year is some factor times the distance, and the distance for now, right? The distance is n is a proxy for distance from star. Okay, so the year we're going to assume at the beginning scales linearly with that, so we just need the scale factor. So we know something about the number of planets, right? It starts at 0, which is bad, right, for linear scaling, because otherwise you're going to end up with. So we need a full linear model, which is to add on a constant, right? Otherwise you'll have a year of 0. So we basically want to know what the range of years is. So
I guess we'll measure the time of a year in hours.
It could be in hours, or it could just be a relative fraction of, let's say, Earth, because Earth is probably going to be in this universe we are thinking. So we might notate that for a minute. So year can be a fraction of Earth year. All right, so then we don't need units because it doesn't matter anyway. So the smallest fraction of an Earth year that might make sense could just be something like 1/10. But I mean, I'm sure there are stars that planets that rotate quicker, but this is all arbitrary. So smallest year is C, right? So we might start off with 10%, and then we want the factor K to be big enough such that the most distant planet has a meaningfully large relative number of years. So again, it doesn't really matter. It could just be, say, 10 or 20 times Earth's year, right? So since C is so small, it's almost 0 already. So really, it's just it's going to depend on how many planets we allow. And I would say we probably allow. We don't want to make it super crazy. I would say we may just allow. We might have a constant here for max num planets is say 6. Okay, so then if we want the sixth planet to have a 20-year cycle, then well, I should have picked a rounder number to make it easier. Let's pick 10. Why not?
Did you do all caps on purpose?
Yeah, constants sometimes, universal constants are sometimes put in caps.
Universal, okay.
To help make them stand out. Yeah. Because this is kind of like a global setting, and eventually these would all migrate into a system of storing global parameters for setting up a data set. So for now it just lives as an individual variable, but eventually you would import like a common set of parameters. Yeah, so, and that could also be true of C. That might have been a reasonable thing to make C, but we'll see. So let's see. So if number of planets is 10, we just multiply that by what did I say earlier? Well, it doesn't matter, but 2 if we want 20 times 20 years to be the thing. So we might make k equals 2. Yeah. Well, so technically n goes up to 9, not 10. So that doesn't really matter, but it's about right. It's all arbitrary. So yeah, so that gives us a year. Okay, so just a simple linear model, and then we'll just need the oxygen percentage. Yeah, so C and K, honestly, when I look at this, actually, C and K are global at the moment, so those probably could reasonably be constants that come outside, and I suppose the same argument could be made that they would be capitalized and named better once they start going further away from where they're being used, but I'll worry about that a little bit later.
Do you think God made the universe in much the same way as
I had plenty of time on his hands to do the planning. I wonder if he was agile. So we could use another float range here to, so this could be called, say, composition. So these are like chemical compositions. In fact, let's call it chem composition. And that is a float range, which this particular one, I guess, yeah, all chemical compositions are going to be a fraction of, say, planetary surface area. So we'll just call these chem, and they are going to vary between 0 and 1. And the distribution of these is probably going to be a little bit more sophisticated. In fact, this might be where we choose a, say, Gaussian distribution for fun, just to be different. And that would mean that we have a... actually, no, that won't work because... I have to be a bit more careful because we need to bound the choices of Gaussian. Gaussian numbers, Gaussian distributions will generate numbers that have a mean and a variance, but they can have arbitrarily large and small like negative values. And they're just very unlikely. So we would want to bound that in some way. So I have to be careful about that. And these are the kinds of things that we have to figure out, right? Because you will want a Gaussian distribution of something at some point, but often it's really important to know that those numbers are bounded between two places for your mechanics to make sense. So yeah, we have to put a little thought into that. And I'm probably spelling... Oh yeah, it's just Gauss, good. I'll check down here. I'm almost certain it just takes the two values for mean, mu and sigma, the mean and standard deviation. So those are technically also, this isn't really a, well, yeah, it's not really a, so the difficulty with writing these types of function signatures is that you get locked into assumptions about how you're going to build them. And so a Gaussian needs additional parameters other than just the range limits to determine what you're going to draw from, right? So even though we want it between 0 and 1, the Gaussian will have to have additional parameters set for the mean and standard deviation. So on one hand, what we could do, I kind of wanted this class to be a catch-all for all of the meta parameters that we would need. So that kind of makes it a little bit harder. This is where we would look back maybe at this this function signature and consider replacing part of it with a keyword arguments, so that becomes flexible depending on the kind of distribution that you have, because it'll all be different, and that will add a bit of complexity in setting up this boilerplate. I will return to that. I don't think it's super interesting to go into right now. So what I'm going to do instead is another kind of hack that you can do, which is to add another a layer here, which will be to make a chem flavored Gaussian that takes the mu and the sigma and returns a call to that value. Oh wait. I need to build in. Yeah, I need to build in the bounds. What am I trying to do? So what I'm trying to do is I want to change this Gaussian here to become something that can fall into place here for this distribution function later on. So that distribution function later on is going to just take the low and the high value. So what I actually want to do is, because this is a factory function, I actually will be returning some other function f that I'm going to build on the fly, and f is going to be, or maybe I should have called it d for distribution. Let's call it dist to be nice. So that is going to be the thing that does take the low and the high, because that conforms to the function signature that I'll use when it's put into here. And the mu and the sigma though are preset, so those are being set at the time of making this function for mu and sigma, but the value might need to lock. So there's different ways you can treat this, right? Because if the Gaussian number that you generate is outside of the range low to high, then you need a policy for, do you just repeat until it is within that, or do you just take the max or the min? And this is assuming that a lot of things. In fact, I might make note of some assumptions. I'll put this in a doc string. Oops. I like that kind of doc string. Mu will always be within low high. So I'm not checking that. And that would certainly be a problem if you try to generate numbers that are outside of the low high. You might never get what you need. But for now, I'm just going to make a note of that to come back to and clean up, rather than
internally.
Yeah. So I'm going to generate a number, and then basically I'm going to make a simple choice here, which is assuming that. Wait. So v might already be between low and high, and if it's not, then I'm going to take the max of v and low, right? So that if v is lower than low, then it will return low. It's a common trick to just box values in, and then you take the min of that against high. So that way, if the so if v is way too big, then that's certainly going to be bigger than low, so you'll get v again out of this inner call. So this thing will end up being v if v is really, really big. But then if it's bigger than high, then high will be the min of that number in high. So this guarantees that you get a number back that is within your limits. And you wouldn't want to choose sigmas so big that you get a distribution that that typically falls outside that range, commonly, right?
What do mu and sigma commonly represent?
Yeah, so that's great segue maybe to adding a picture here so that I can draw that out. Okay, so I'm trying to use this pen. So you've got a distribution. Why doesn't this pen draw? Oh, just lagging. Still setting up. Oh, there we go. Hang on a second, let me kill that. Okay. Oh, it's doing that thing again. So the pen keeps jumping off the board. Alright, here we go. So, mu, oh god, trying to draw Greek with this pen is a nightmare. So mu is the mean value of the Gaussian distribution, and is a classic bell-shaped curve, which I'm not going to do justice to. Probably, it's probably a little bit pointy. Anyway, but that is an infinite distribution that goes on forever, right? Positive and negative. But you've set mu someplace, right? So, and this is going to be our v value. And so you've got mu, here's the mean, and then sigma measures the standard deviation. So that is little sigma. Okay, so I think that's 30%, 30-ish% either side, if I remember right. So you get about 60% of the distribution lies within the first SD, standard deviation. Okay, but the problem is, because that's an infinite distribution, you actually want numbers between two places. So it could be 0 and it could be 1, and mu may be, somewhere in between those. So sometimes you're going to draw values outside of that range, and so you want to have a policy for what you're going to do with those values. You're going to have them limited to the ends, or alternatively you could throw it away and re-pull from that distribution until you get something within that range, and then you'd have a loop. I'm not going to put a loop in there just yet, just because it's possible that you could set mu to be outside this range, and then you might get into very long loops where you almost never draw values in the right range and it will just go in an infinite loop. So without adding all kinds of sophisticated stuff, I'm just going to box those numbers between these two values. But does that clarify basically what I'm going to do? Yeah. Cool. Alrighty, so that's my factory function, and that way I will need to make an instance of that here, but that does mean that we'll have to preset the mu and sigma for now. So that's not ideal, and we'll come back and fix that another time. But I'm just going to set the percentage to be 0.5. I mean the 50%, which is 0.5 on the scale, as the mean, and then the standard deviation I'm going to make 0.25. Actually, this might not be so bad, because some planets might have none of something, and so if it hits the low end, then that's good. But the flip side is that it might also make some hit the other end, which is 100%. And that's kind of crazy. So maybe it's really bad to make these numbers so large, actually, because the percentage content of a particular chemical is probably very low. So we might even knock this down an order of magnitude and say that 5% is a good average to have. That way you're very unlikely to have things. In fact, we may also make the largest value for one of these percentages, even though percentages can go to 100%, it's completely unreasonable for these things to be as large as 100%. individually. So we might put a cap on it and say 0.1 instead.
0.1 meaning 10%.
Yeah, 0.1 being 10%.
Well, what if let's use an example, the surface area of the water. Like in Earth's case, that would be 0.71.
Sure. So that might not be for a chemical then. This is exactly the kind of things that we'll have to figure out, right? Because there'll be different kinds of thing that would have different types of limits that are reasonable under different situations. So for instance, if we were just measuring carbon, or if we're just measuring iron or something, I mean, first we have to decide whether we're doing this based on, say, what's observable at the surface versus composition of the planet as a whole. But water might be surface water, and that might be percentage coverage as opposed to percentage composition per se. And so you'd probably want to build a different type of object to accommodate that different kind of range. And that's exactly why I think doing this planning is helpful to make those kind of things pop out, right? Because otherwise, the first thing that happens, you'll generate all these planets and go, oh yeah, we accidentally had a planet that is 100% iron and 100% something else, right? So this way, if you make these things really small, you can never have to worry about them adding up to greater than 100%. Because presumably there's going to be a whole ton of other stuff in there that we don't want to worry about. So just make the maxes of those really small, and then you won't even have to worry about it. So, but yeah, that's a good point. So I might even make that to be something like average is 1%, and then I'm going to have to make the standard deviation way smaller. And we'll test that. We'll do some trial runs just to get a feel for whether that type of number feels good. So yeah, so actually that should be runnable right now. So we have this object called chem composition now, and let's do some measurements and see what kind of numbers we get. And I'm going to make a whole bunch of them. So in range, let's make 10 of them. So they're maxing out quite a lot, right? They're hitting. Oh, is that true? No, then I'm sorry. They're not maxing out a lot. They're actually staying pretty close to the mean, which is 0.01. So maybe that's too little variation, right? So maybe I want my standard deviation to be a little bit more wide than that, because we want some to get up maybe a little bit higher. So right, good. So now some of them are hitting 0. And that might be good, right? We might want some of the planets to have 0 of a thing, just like straight up 0, as opposed to having varying types of diff. So let's see here. I am just gonna.
So the chem composition object depends on float range and behaves one way, and then we can set other objects using float range too.
Yep. So that one looks pretty good. So that one, so there's an instance here that was 5%, right? And another instance that's 3%. So it's a good starting point, right? Sort of ballpark. And since this was for oxygen, maybe that was a bad choice, because that could be something that you would only observe from the surface. But yeah, we could flip oxygen to be something maybe more like iron composition or something like that. But we could also make a different one. Now that we are getting a feel for this, we could say we could make one called surface composition. Right. So here we would copy this structure. Oops, lost my equal sign. And instead of calling it chem, we might call it surface. And this could maybe more realistically go up to, surface or atmosphere, maybe atmosphere, atmos. These are observables at the surface. And so these could conceivably get up to 100%, but maybe we'll still cap them at 90%, because we're likely to have more than one, and so we might end up, for those, having to do a check that we don't draw 3 numbers that add up to more than 1 if we have 3 different atmospheric components. We can come back to that later. So now we might pick something around, say, 40% as the mean and 20% as the standard deviation. Okay, so now our oxygen value for each given planet that we're going to pull out is going to draw, just like we were using it on the other side. We're going to create an instance of that, and that's going to be our value. I could have inserted this directly into here, but the fact that we've named it for now tells you what it is here. So it's like having a named parameter. So anyway, that's a thing. We haven't figured out the x's and y's yet, but we should probably test some stuff. So I'm going to put in a test value for x and y, and I think it might be time for us to see if we can build a system. And what we do need to do is add the planet to the system. So there are planets, there's a list, and we're going to append the planet that we just built to the list inside of the system object. And then I think we might be good. So make a star system with 5 planets and get back a sys. And I've already made a mistake in my naming. Oh, maybe I didn't execute this. It's the trouble with Jupyter notebooks. You forget what you've actually executed. So let's see. Alright, apparently that's happy. So system has some planets, and those look ugly because I didn't give them any string that shows you what they are. But that could be something we can add. But let's pick a planet and look at its oxygen percentage, and it is 20%. All right, so that's a beginning setup for how to build some surrogate data with some simple distributions, and a couple of tests to go with it, really. What do you think so far?
I think it's really interesting, and just based on the fact that we just generated these characteristics, can we just look at what it looks like in a data frame?
Yeah, good idea. So let's go back and import pandas. In fact, while we're at it, let's get our matplotlib. And so if we're going to use pandas data frames as a way to organize the data for visualization purposes. And the data currently is all trapped inside these Python objects, which is great for building and manipulating things algorithmically. It's certainly a lot less good for seeing what you're getting out. So yeah, we want to sort of introspect this data, and so what we might do then is we might make a function that extracts a data frame from this object model, so that it makes it amenable for visualization.
And ultimately, in the data prep phase, when we're creating this to send to the databases and things like that, I'm guessing we'll be using the data frame to see.
Also a good point, right? So at some point we would generate this data algorithmically, but then export it to populate the databases that the folk in the session would use. So yeah, absolutely, we'd need to translate it one way or another, whether it goes via pandas data frame, or whether we just we might just write a function that writes out SQL inserts directly from the object model. But yeah, either way, it needs to be extracted. So that's a great point. So yeah, we are going to, I didn't really do this earlier, but I'm going to use a little markdown here to extract data for, let's just say, to a table. And from object model, it gives you a nice heading in a markdown cell. So this sounds like it's going to be a function. So we might say call this object, or well, we'll just do it at the system level, because at some point there'll be a group of systems. Actually, yeah, maybe we should think about this. So there's going to be the universe is going to be made up of systems. So there might be one more thing that we do first, right? Which is to make one more quick function to make the universe. And so there'll be the number of systems that you want in that universe, right? And so that allows us to very easily use the same pattern. You'll take a range in that, and you will make a star system. So this is layering up the tools that we're making. And we're immediately faced with choosing how many planets, right? And that's cool, because we kind of wanted the different systems to have different numbers of planets. So we now have to create another random variable that generates that. And let's again make that one uniform. So back where we said planet size, so the trick here though is we need an integer. So I might just hack that in right now, just because we've kind of already seen something more interesting about it using floats, but I'm just going to use rand_int, and we know that there should be, I mean, some star systems won't have planets, so we don't know whether 0 is a valid value.
Is it not?
It could be. I guess we could let it be 0. And then that's why we have this constant max num planets, right? Because you don't want to hardwire that into this function, because you'll lose track of where that's defined. And that might have consequences for other functions, right? So naming it something will allow you to not have these weird sort of side effects that you just don't understand why something's broken later when you try to change values and it doesn't update somewhere else. So we've made a system with that many planets. And for now, we can just call our universe a list, which is a very basic. Yeah, I guess we'll define that internally. Uni is a flat list, an empty list, and instead of calling this thing star, I'm just going to append the results of calling make star system. It's unnecessary to have another variable there. And then you return the universe, and that's just a list right now. So later on we'll probably make that a class. It might have some other metadata associated with it, but we have no idea what that is right now, and as we're just getting started, we'll just make a note that the universe is just a list for now. Okay, so let's go ahead and make a universe. Oops. And we'll just keep the number not too crazy. And then again, we should test this. So maybe this, I'm in two minds. So some testing inside of the notebook is possibly good, because like I have up here, this is a reminder of how you can access the attributes inside of that object. Mm-hmm. It almost acts like documentation. Whereas if I throw it in the console, that is ephemeral and that'll be lost. So I am actually tempted to leave a note of that. So let's just pick a random system, and then I can essentially do the same type of biz that I did up here.
And console, by the way, that's exclusive to Jupyterlab. You don't get that in Jupyter Notebook.
That's correct.
Okay.
It's only in the lab. Yeah, there's lots of bells and whistles in the lab that are only in the lab, and I think it's wonderful. I don't know how many planets are in the system, so there might actually be none. So I have to be a bit careful. This could backfire, but I certainly will find out. I guess I'll find out what the last planet is, and that might be an error. Fortunately, there were planets in that system, and I have a value. So that's how we're going to use that for now. Okay, so the object model really is a universe, right? The universe is the top level object for our data right now. So this is where I want to turn a universe. So the whole reason we took that backtrack to make a universe is I was thinking about naming this function. And I was thinking about, it's like make table or something. But really, I think about it's converting the object model to a table, and thought, well, what is the name of that object? And I was thinking system, and then I realized, well, it's not really system, it's the universe of systems, and so we haven't defined that yet. Mm-hmm. So ultimately, you're going to want one function that takes the global sized object and puts it to a table. So that's going to take a universe as its input, right? And at the end, we are going to, for now, assume that we're going to return a data frame, which we haven't defined yet. Mm-hmm. So that's our kind of signature and structure for the function. It gives us a heads up that we're going to create a data frame and return it at the end as df. So what do we need to make a data frame? So you can do it from different ways, right? A common way is a dictionary. But because you have an object model, we actually will have to iterate through the objects in order to pull those values out. And so we'll have to build intermediate data structures like lists or arrays to feed in to these things. And we have to think about this, and this might be a time to go back to the diagram here and start over, because what you're going to realize quickly is that a tabular structure for this needs a little bit of forethought, because, for instance, systems may have no planets, right? So how do you want to represent that in the data frame? Do you have empty values or whatever, right? And if there's, I'm getting ahead of myself, let me draw a picture. Delete. That is taking a minute. Let's start afresh. Okay, still loading. Okay. So, you might have a row being the rows and columns. So you might have system 1. Oh dear, that was there we go. System 1, and so there are some things that will always be present, right? So size is always there. I drew that too high. Yay. Okay, let's see if this is a thing. Can I move that? Ooh, nice. Nope, nearly.
It's finicky on this system.
Yeah, sorry. First time we've really tried to use this in production, as it were. Okay, that's much better. Okay. Here we go. Do. Oh, what a fantastic straight line that is. Let's try that one more time. Okay, so we've got size, and so there's always going to be a size, right? So that's kind of a given that there's going to be a size. Oh wait, what am I doing? This is system, so I blew it. So that's not even that's not even a property of a system.
Yeah.
Sorry. Let's try that again. So so the coordinates, right? So let's just say x.
system contains the coordinates.
System is always right. System always contains an x and a y. So that's a definite attribute that will always be present. But then how are you going to store the planets associated with that in a data frame? Because there might be 0 planets, but how many planets? So it's good that we predefined a maximum number of planets, because one way to represent this in a tabular fashion is to have that number of entries, and those will be blank, I guess, if there is no planet there, right? And you can also have like, and you can have a value here which would be like number of planets, and that can be 0. So that's a given. And you're not going to store. Well, you could have a multi-index table and like store all of the planet data inside of a substructure of that table, which is not flat and is not immediately transferable to SQL, but it would be transferable to JSON, right, which can be nested. But I'm thinking that we're going to end up with SQL, so I would rather maybe make different tables for systems and planets. Okay, but in any case, the systems will have to refer to the planets, right? Because you're going to want to look up the planet for a given system, and certainly in SQL land, that's what you would be doing, right? You'd be writing a query that joins tables, probably, right? So you're going to need keys and so forth and identifiers, so that once you have a system, you can look up the table for planets somewhere else based on that key. So you have different choices here, right? You can. This is called long or wide. So the long format would put all of the planet IDs, as many as there are, in columns. So you got PID 1, planet ID 2, up to n of them. Okay, and then they may be blank. So then you can have values in here as you see fit. Okay, that's the long format, and you just list them all out. That's probably good. Then you only have one record per system, and because we have a fixed number, that this is sort of all bounded and constrained and so forth. But for instance, if you didn't know how many planets you were going to have, or you're going to let that be arbitrary, then you might want to do, I've probably named these around the wrong way. I'm trying to remember which way around is long and which way is wide. This might be wide.
This one seems wide.
This one is wide. Yeah, now I'm thinking about it. Yeah, this one is wide. It's a little weird because length I'm thinking of going left to right here, which is what's throwing me off. So yeah, this is wide. There we go. So the other format would be long, which you have multiple entries, and then you have naming issues for your rows because you're going to repeat data. And here you might not even have NP here. You might just have PID 1, right? And then you would have another entry under sys. This isn't playing nicely. For the same system, and then you would possibly repeat the fact that it has coordinates, which is another issue.
They'll all be the same coordinates.
They would all be the same coordinates, but you would put a second ID here. Right, so that's the long format. And there are all kinds of tricks to, you might have separate tables for the parts that are common, and then you might not repeat these. Right, you might store those in a separate metadata table, and then have a planet table that is long versus wide. But I'm inclined to pick the wide format since we're keeping things simple and have a finite number of planets. So I think that's what we'll do. Then that way we'll always have, in this case, 10 additional columns that we may not use, but they're only going to contain IDs anyway, and that's not a huge waste of space. The long format can sometimes be better value for money in terms of storage space, especially if if n here is really, really large. You don't want to have 1 million columns for every row, especially if it's sparse, right? So there's all those kind of design choices. well, that's getting pretty deep into schema design that I don't think we need to worry about. So we're going to go with the wide format. Okay, so we're going to build up rows, right? So I'm just going to start with a list, and we'll make the data frame at the end based on a set of lists that we have. I'm also thinking that we're probably going to end up with multiple tables the way we're going. So we'll start with making one table and get it right, ignore the others maybe, and then we can, once we've got the pattern, it'll be quicker to repeat, to do all of them. So always start really small and build out. So let's see, let's just well, the universe is pretty boring in terms of metadata because it just has a list of systems. So let's start from the inside out, and or maybe even just pick systems as a starting point, because that would be the interesting one. So our universe has at least, let's see, the universe is just a list. So we're going to assume, for the sake of getting started, that there is a system in that list, and I'm going to build rows for, I'm going to call them wide rows for this system. So I'm going to start with a row that we're going to have, actually star systems probably have names, which we may not have defined yet. I think we may have named something else, but not the... Nope, we didn't name anything except for float ranges. So that's an oversight. So naming is going to be important. So let's just drop in some names here, and I'm going to have to fix... Okay, so that's great, but have to update. We have to generate a name, which for now is just we'll just call it sys1, and then the planet name is going to be P, and I'm going to add on an integer, so that integer position will be part of the name, and I'm probably going to regret changing it from 0, so I guess we'll just let P0 be the innermost planet. I'd want to call it P1, but indexing conventions I'll eventually get confused when we do testing, at least. Maybe for public view you would call that P1 rather than P0, but I would rather do that at the very end of the entire design. Internally keep it more consistent and start with 0. Alright, so we should check that that still works and that I haven't done anything stupid. So that's fine. I should check that my system has a name, or that my planet has a name. Yep, P0. Okay, good. So my rows will be made up of the system name, the system coordinates X and Y.
Looking up the Faker library, which
I've heard of it. Yeah, I haven't. I think I looked at it a few years ago. I would love to look into the Faker library again and see. It's got some pretty neat things in it.
Yeah.
And there may be some overlap with what we're doing.
Yeah, there's some name generators and
yeah. I thought this was a good exercise in sort of looking at it from the ground up, but I'd love to reuse some of the stuff from one of those libraries. I was trying to think of that name the other day and I couldn't, so thanks. Faker is... Yeah, could you post a link to that? I think I may have used it a while ago. So let's see. So we've got names, the coordinates, and then we've got this long format for the planet IDs. And for now, we might have internal IDs.
Well, I got smacked here for posting a link.
Oh, okay. Yeah, I'll have to make you a moderator. Yeah, we haven't connected that up yet.
Okay, well, I'll send you the link.
Yeah, if you send that in the, you can even email it to me and I can pop it up.
There you go.
So is that in the Hangout?
Yeah, I'll just put it in the Hangout.
Okay, let's make that happen.
It's here now.
Mm-hmm. I assume that I can post a link. Yikes.
You just got hit?
No, I didn't get hit, but it's. Let me just go to it first, and then it's got a. The link is modified by Google because it wants to track clicks on their Hangout links. So I need to go through the link first, so that I can copy paste it. There we go. Okay, good. Yeah, we'll fix that for next time. Okay, so we have a fixed number of planets. So I'm going to write another list comprehension here because there has to be an entry for every planet, right? Because every row must have the same length for this to work. So we're going to have range of max num planets. And for now, I'm just going to have the planet ID, which I'm going to use the name as a surrogate for the planet ID since they are unique. So I need my systems planets list, and I'm going to index that with I and take its name. Now, if you think about this, this could go horribly wrong because there is a variable number of planets. Right, so I'm trying to iterate through every planet in max num planets, and that might not exist. And so what I might replace this with is the length of that list. In fact, if I'm going to do that, then I actually don't need a numerical range anymore. I would just iterate directly through system.planets. I thought I was going to be smart and maybe have a conditional in this list comprehension to check to see if something exists, but it would be too late the way this is written. So this indexing would fail before you get to find out whether there's something there. So it's actually going to be smarter to just move this to become p.name for p in sysplanets. Because in Python, you can iterate directly through an iterable. All right, so yep. So now we have the opposite problem, which is that we will need to know how many planets are left over that are missing to fill out the row. There's going to be missing values.
Well, if we go with the long data format, we wouldn't have that worry.
That's right. We wouldn't have that worry in the long data format, but there are also ways to set up the data frame creation so that once you've set the schema for the table, it will populate with null values for missing stuff. Okay. So that might work out.
So 1, 2, 3, then nan.
Right, right, and then we'll have to decide, what to do with that later. But yeah, so that pandas is smart enough if you ask it nicely. Although I've forgotten whether that will work just off the bat, but we'll see. So yeah, the row is simply just that. So we've built one row from one object in the universe. So we will just have to iterate through and build a list of rows. So we don't really need that anymore. We'll just say row list is empty, and then we will actually. So we created sys. I'm just gonna, now that I'm starting to see the pattern, I'm just gonna build a loop. And then build a row for each system, and then append. And I could have appended this directly, but whatever, it's fine. All right, so now I have a row list. I need to decide on the way I'm going to construct this. So we have different sort of options with a data frame. and I didn't really think about this much in advance, so I'm forgetting what would be a good way. So if you've got the rows already, what's a convenient way to build a data frame from rows?
If you have the rows already?
Yeah, if you got it in that format as opposed to defining them per column.
As I do a dictionary, and the row is a list, right?
Yeah.
Yeah. So if you're doing a dictionary, then you just do the column name and. Oh, you're saying you have full rows?
Yeah, we have full. So I built it kind of that way around, right? That's exactly where I'm having to think about what to do. So we can flip and you know.
You could do a loop. And
yeah, you could.
But that's not.
But I think there's going to be a pandas way. Yeah. So there's a really good pandas thing about building row by row. There we go. See, these things are always commonly asked. So let's just see. Yeah, let's see what kind of answers we have here.
I'll look at the manual, but I don't think I actually looked at that before. I'm not sure that it's well documented.
Mm-hmm. Okay, good. So
You got it.
I think you can build a series out of the pieces, and well, I guess yeah. So lock. Okay. Yeah, I guess you just build you just build it empty. You just build it with the columns. Yeah, I forgot you could do that. So all you need to provide is the columns and an index. So the columns are going to be sysname, let's say, and then the x and y, and then we're going to want to generate. This is where we can generate all of the planet IDs. So we're going to have planet ID n, and that will be an integer for n in range max num planets. Okie dokie, and then the index. Index is going to be the sysname. I think that's right. I'll indent that a bit more so it's clear. Okay. And then, yeah, so now we would loop through for row in row list. Oh, yeah. I guess my system name, I guess we'll need IDs at some point. I'm sort of getting ahead of this because the name would probably be a column in this, and the index would be an ID. I suppose I could make it ID. I don't think I need that as a column name for it to be ID, but then I'm going to need to know the index, and I'm just going to use the index for now as a surrogate for the some kind of hashed ID that we'll have later. So to do that, I'm going to enumerate my list, and that gives me an index to go. All right, so df.lock, the index is going to be my row, and I think it might just take a list. It should take any iterable and consume it, but we're about to find out. Yeah, so what did I do wrong? I could have sworn that so this is what happens when you don't test stuff. Oh, because I need to remake my universe because we changed the naming. We added the naming since I created that object. And something else. What did I do? Oh, okay, see. I stored the coordinates as a pair, as opposed to x and y. Well, it's an object model that we're not using in production. I'm not sure it would matter to store this individually as x and y. We're gonna have a very small number of attributes. I don't think it's going to pollute the namespace too much to separate these out, and I don't think it adds an awful lot of value to keep those as a pair. If you wanted to use them as a pair at some other place, you could put them back together as a pair. I don't know, not sure, I'm agnostic, but keep it simple, I'll split them out. Not sure. If I'm not sure, it probably doesn't matter.
Now it is already such that X and Y, they're going to be differently assigned by system already.
Oh yeah, I mean right now because we're just setting up a test set, I've forced all of the X's and Y's to be constant.
Okay, they're constant, right?
Yeah,
okay.
and that would be something that you might add in a comment here for later, which is like generate random XY pairs, right, for sys coordinates. Yeah, so that's a to-do for later.
Yeah, because then we can start plotting it.
Right. So this is just getting the skeleton, and then we can go back and make that stuff happen.
I was just seeing if I had missed that component of it.
Yeah, absolutely right. So I'm probably missing some other stuff. So what else am I doing? Oh, it requires a collection. Okay, so it does require index to be a list. Sometimes these things let you pass singletons and then it converts it internally. What else am I doing wrong? Cannot set a row with mismatched columns. Oh. So apparently it is a problem it is expecting this to be, so we will have to generate the slack amount of data. So it doesn't just force. There might be some function that we could use that fills in the blanks. I thought that might be a problem. So we might actually have to just be a bit smarter. It'd probably be easier to just add it up here and know ahead of time how many planets there are. And so the extra planets would be the remaining between the total and the number that we have. So that's the number that we have to generate additionally. So the names will come from any that are in that first part, and then any excess names are going to be blank. And there are extra planets, number of those. Doop. There we go. So, oops. So I totally messed up doing the, there's apparently a row even for the system ID, which is weird. I have to look up what I'm doing wrong to ensure that that isn't its own row. But anyway, you can see now we've already begun to visualize some planets. Now these planet IDs aren't unique. They're only unique if maybe you, oh whoops, yeah, the system name is also constant because I forgot to update that. So yeah, you would start adding layers here where you would parameterize this with some kind of unique system identifier, and then you can add that into the name or something like that. Or you generate actual names and then you just keep the IDs on the outside. We'll sort of come up with that later. But yeah, right now all the systems are named the same, but you can see them having different number of planets. So there's one table that would give you a lookup between a system name and a planet name once these things become unique, and then you would look those up in a second table. That is, so this is a system table, and then you build a planet lookup table. And that planet lookup table could be global, like you could flatten it across all systems, and then you'd be cross-referencing from the planet ID within a system from the system table, and finding that planet data from the global planet table, because they'd all be uniquely named. They'd all have unique IDs that you wouldn't have to worry about that stuff.
Really cool, especially when we figure out how to set the value for X and Y and iterate through those planet names, then we can already have our starter.
Yeah, because you'll be able to start visualizing these. I mean, because one of the other things we might do in the next broadcast would be making some fake data for the geometry of this 2D space and deciding how we want to distribute the systems, because it might be interesting to cluster, allow clusters so that it isn't just too uniform, and thinking about the types of dynamics in the game. If things are moving between systems and there's differing distances, they might stay within clusters, or we might add all kinds of geometries that might promote people thinking around, well, they're more likely to travel along this kind of line because in that line on that space there is there's a higher density right? Like filaments, if there are filaments.
How about just for fun, for x and y, let's set like NP random and random between 1 and 10.
Sure.
And then see what it looks.
Yeah. That sounds fine. So we'll just hack this in. We'll actually make it float, I think.
Okay.
And we'll put it on a like a grid from 0 to 100.
Cool.
In fact, let's see. No, I think it'll look prettier if we make it Gaussian. So that'll be fine. And let's give them a slightly different distribution, so you make me look a little bit more like a galaxy. Yep. So we won't worry about the naming. The names are kind of irrelevant right now. Let's remake my universe. And there we go. So yeah, so you've got a bunch of coordinates. So you see there's an outlier here. There's this crazy outlier at -25. But that's fine. Yeah, so I can't remember off the top of my head. I don't normally plot these things like this. So there's a nice little trick in here. You can put a question mark and it'll actually output the format of the signature. But that's just like a full plotting API, so I'm not sure that that's what I want.
I guess if you could do universal table, uni, then dot plot, and just immediately plot it. Except I don't know how to handle that man.
Yeah. We'll need to. Well, so here's a simple trick. You can actually write queries, which might be overkill for this, but something that I kind of like is you can. Oh, I didn't like that. Oh, oops. Silly boy. Right. I didn't assign this data frame to anything, so that's not helping, because there is a plot associated with, but I was actually accessing the pandas library rather than the object that I just built. In any case, query you can write and it will filter arbitrary things, quite like that. But there'll be a cleaner way to do that once I've recalled how to build that index properly. But that gets you the cleaned up data frame. But yeah, actually that does have a, so there is a plot, I think, and then you have to tell it the coordinates that you want. So fortunately those actually happen to be x and y. So I think, I don't know whether that draws lines or what, but we can also see if there's like a
yeah, defaults to a line plot.
Yeah, so we just have to look up the symbol or whatever styling it needs. Does it? Oh, it's probably not in this documentation. Oh, it's down here. Kind equals. So what is the kind for just dots? It is scatter.
Yep. So I think it might be x equals x and y equals y.
Possibly, yeah. It's probably safe to do that just in case. If they are the first two arguments of the function, they will default to that. But it probably is safer to do it that way. So I'm down with that. There you go. We have a universe of 10 things. It's probably a lot more interesting to make a universe of at least 1,000 things and plot those. And let me make that much more interesting to look at. What do I want to say? 15 by 15. And then these all take axes attributes, which if you just built an axis that you control the properties of, you can pass it to your favorite plotting method in pandas and it will use it or not. What did I do? Oops. Here we go. Ta-da!
Look at that universe.
So we have a little universe of systems.
just fascinating to look at that and think about all the planets that that's associated with and all the properties that we're going to be distributing among these.
Yeah. So graphically, this is completely flat, but it's beginning to give us some visual insight into what's available. And one of the exercises that might happen during an actual hackathon would be if people start if they start reverse engineering this data. When they start to learn about what is inside of these things, there are ways to augment plots like this with hover tooltips and other kinds of things that make these clickable.
Within Matplotlib?
To some extent with Matplotlib, but you might get people to use Plotly or Bokeh or something like that. And it's really rather easy to create widgets that make a kind of interactive system. And then if you have less technical people on the team that you're working with, they can be interacting with an interface that you can provide to them without doing all of the programming.
Yeah, if you have a good visualization expert on your team and they've got Plotly and Bokeh, I think that's a big competitive advantage for the hackathon.
Yeah, because then people can ask questions in a more naturalistic way and explore it at least partially visually. Like at the end of the day, you're always going to end up needing to extract some actual data and put it into some kind of computer readable format. Mm-hmm. But there's always going to be a component as well that is this high level. So yeah, this is kind of a prelude to what that could be, and it's pretty cool.
Yeah.
So in a sense, we're almost like reverse engineering these very loose ideas that we have in our minds.
Yeah.
Right, and we're trying to reverse engineer anything of that kind into a data structure, and then we firm that up, flatten it out into SQL, and then let everyone else do the same thing from that SQL data.
This is an awesome start.
Yeah. So I think this might be a good stopping point.
Yeah, I think so.
Yeah, so we'll probably do one of these again soon. But yeah, there you go. That's some code. hope it was fun. And I hope the music was palatable and
good music for this. For this, I hope that anybody watching this, at least somebody's played Master of Orion, because it feels like we're creating Master of Orion again, that video game from 1995.
Yeah, it's pretty sci-fi. It's good. All right, see you later.